In this lesson, we're going to recall the basic vocabulary associated with the solubility product, including KSP, saturated, unsaturated, and the common ion effect. We'll also practice some of the more basic calculations that rely on the solubility product, including the molar solubility of a compound in pure water and in water containing a common ion. The solubility product expression, also known as the KSP, describes the dissolution of a solid compound to give a saturated solution of its component ions. In this example, we're asked to calculate the molar solubility, X, of lead 2 iodide in pure water. How do we know that it's in pure water? Well, when we write out our ICE table, where I stands for the initial conditions, we see that our initial concentration of ions is 0. C stands for the change needed to achieve equilibrium, and E is the equilibrium condition, or the sum of the initial and change lines. The change in our dissolved ion concentration is some amount X, because we don't know how much solid dissolves to achieve equilibrium, but we do know the ratio of the stoichiometric coefficients. So we can say that X and 2X molar concentrations of lead 2 and iodide ions dissolve, respectively. Our equilibrium condition also assumes saturation, or that the maximum amount of solid that can dissolve has dissolved. Initially, though, our pure water is unsaturated in the ions contained in our solid, so we have to figure out how many ions dissolve to make a saturated solution in equilibrium with the ionic solid. This is our molar solubility, X. Next, we have to write out the KSP expression, plug in values, and solve for X. Recall that the law of mass action allows us to say that lead 2 iodide solid dissolves reversibly to yield 1 mole of lead 2 ions and 2 moles of iodide ions. So this equation can be rewritten as KSP equals the molar concentration of lead 2 ions times the square of the molar concentration of iodide ions. It may seem counterintuitive, but we do have to account for the dissociation stoichiometry in both the ICE table and in the KSP expression. We plug in our value for KSP, X, and 2X quantity squared. We see that a solid that dissolves to give 3 moles of ions typically results in a KSP equal to 4X cubed. Solving for X, we see that the molar solubility of lead 2 iodide in pure water is 0.00125. Note here that we can retain an additional uncertain digit as long as we indicate the uncertainty by subscripting that particular digit. This may be useful if you have to carry out more calculations. Now, keep this molar solubility in mind as we work through the next example. What if we wanted to calculate the molar solubility of lead 2 iodide in a solution of 0.030 molar sodium iodide? Here, iodide is an ion common to our dissolving solid. So we know that our solid is going to be less soluble compared to the molar solubility in pure water. Let's prove this fact by working through the ICE table. The initial concentration of lead 2 ions is still 0. But now we have a background concentration of iodide that is 0.030 molar. The change line remains the same, plus X and plus 2X, but our equilibrium line is now X and the sum of 0.030 plus 2X. So how do we handle this calculation? Can we make any assumptions about the size of X, 2X, or 0.030? When we drop our equilibrium line into the KSP expression, we see that it's to our advantage to assume that 2x is small compared to the initial iodide concentration of 0.030 molar. This allows us to drop 2x and simplify the expression so that we are not solving a cubic equation. Solving, we see that the molar solubility is 8.8 times 10 to the negative 6th molar, which is definitely much smaller than the value we got in pure water. This shows us that indeed the solid is less soluble because less of it dissolves when there's a common ion already present in solution. Here's one for you to try. When working through equilibrium problems, it's easy to treat every problem as though an ice table is required. This problem is different, however, because one of the equilibrium ion concentrations is given. So how do we solve the problem? We find that we only have to drop the given concentration into the equilibrium expression to solve for the missing quantity. In this case, we're looking for the concentration of the iodide ion. Try solving this on your own now. Did you get 8.9 times 10 to the negative 3rd molar iodide? If not, this would be a good question to bring to class to ask me or one of your classmates about when we continue practicing this type of calculation. That's all for now.